last class we have derived the expression for solution of LQR problems. Let us discuss briefly what is LQR problems. So, our problem is to design a controller, to design a feedback controller or control law, which is described by u of t is equal to minus r inverse of t B transpose of t P of t into x of t. We assume the states are accessible, measurable for feedback purpose. This control law will minimizes a performance index. What is this performance index? Half x transpose T f, f T f, x T f. Then this is the call is terminal cost, and also T 0 to T f half, then x transpose T q of T x of T plus u transpose r of T u of T whole bracket dt. So, our problem is to find a design a control law u such that this performance index is minimized subject to the condition, subject to the equality condition, subject to the condition x dot of t is equal to a of x t, a function of x t plus b u of t. This is our problem, and we have derived the expression to find out the control law u of t, and q of t, this is q of t, which we have assumed is a positive semi definite mean, and r of t weightage with the input matrix input, and this q is weighted with the state vector, and r is weighted with the input vector, and that is positive definite matrix. And we have derived the expression to find out the expression for p of t, agree, for a finite time interval. Now, we have seen to solve this control law, we need to solve a what is called dynamic matrix Riccati equations, dynamic matrix Riccati equation, that we need to, and this is nothing but a set of dynamic equation, which is coupled to each other, and in general it is a nonlinear differential equations. So, let us write the what is called the algorithmic steps, that how one can solve the finite time regulator problems, the algorithmic steps for LQR, finite time, that is finite time LQR problem, finite time LQR problem. So, first step 1, solve the what is called dynamic matrix Riccati equation. Step 1, solve matrix dynamic Riccati equations. Okay. What is that matrix Riccati equation? If you recollect this one, P dot is equal to minus A transpose of t P of t plus P of t A of t minus P B P of t B of t R inverse B transpose of t then P of t plus Q of t. This equation we have to solve it. Since we have considered P is a symmetric matrix, one can easily see from this expression that since P is symmetric matrix, one can see from this expression, then we need to solve n into n plus 1 by 2 differential equation, first order differential equation n into n plus 2 by 2, since P is a symmetric matrix. Agree? So, this differential equation are dynamic in what is coupled in nature to agree, and not only this, they are coupled, and in general it is a nonlinear. Agree? So, this set of different nonlinear differential equation we have to solve it, that is the first step. This with the boundary condition that P of T f is equal to f of T f, and f of T f is nothing but the terminal cost weighting function, and this is the cost is your what is cost is integral cost functional, this whole part integral cost functional. So, with the knowledge of this boundary condition, we have to solve the P dot of that is expression, this expression, to find out P of t, and that we have to do what is called backward integration in time. We have to do backward integration in time, this one. So, next step, once you solve this one, next we can easily implement the what is our control law. Control law u of t is equal to minus r inverse of t, agree, then B transpose t, P of t and x of t, and this if you can write it, this whole thing is k of t and x of t. It is just like a state feedback, you can say that information of state it feedback, and we are generating the control law, and that k feedback control law is varying with time, and this is the second step we can implement this one. And as I told you, this solution you have to do backward integration, you have to store all the information of Riccati matrix P, and then in second step offline, this is a offline computation, you have to do it, then store it in a matrix, and then you compute u of t online. Then step 3 is then solve the optimal state trajectory x star of t by using this equation, x dot of t is equal to a of t x of t plus b of t u of t. Okay. This u of t we can compute from step 2. So, this way you have to solve it. And now, question is, suppose the matrix A of t, B of t is time invariant, that means this parameter does not change with respect to time, and also weighting matrix Q, state weighting matrix and also input weighting matrix does not change with time, then you can write in place of A of t, in place of A of t you can write A, in place of B of t you can write B, in place of Q of t you can write Q, and in place of what is called R of t you can write R in this expression, but still it is this expression is valid for this one. Now, one may be interested to find out the what is called the optimum cost. So, if you want to obtain the optimal cost, obtain the optimal performing index value, then J star is optimum value is half x transpose T 0, P of T 0 and x of T 0. If you know the initial condition of state, and since we have solved the Riccati equation, matrix Riccati equation, agree, and we have solved it in backward in time, then store the value of P of 0 at P at time t is equal to 0, this store. Then you can compute the optimal cost of the performing index over the interval 0 to t. What is the performing index? That performing index is that one, the value of j you can compute over the time t is equal to T f. What is the expression for 0 to T f? This expression you can find out with this expression. So, we know the algorithmic steps of this one. Now, we will see the what is the sufficiency condition to get the nature of optimality. Sufficiency condition, sufficiency condition for the optimality, to check the optimality means whether the function, the objective function is optimized in the sense is maximized or minimized. To check that one, this sufficient condition you have to consider. We check the sufficient condition. Let us, if you recollect that our Hamiltonian matrix is this is formed from the system matrix knowledge and also performing index, state and weighting, state weighting matrices and the input weighting matrices expressions. So, this is the half x transpose of t, u of t, x of t plus u transpose of t, r of t, u of t. This is the first part which is formed from performing index plus lambda of t transpose A of x t, x of t plus b of t, u of t. And you recollect, you may recollect that the what is called Hamiltonian matrices form a function which is free from its the x dot derivative, agree this. So, this Hamiltonian function to examine is the nature of optimal control law, to examine the nature of optimal control law. What does it mean? To nature the optimal control law means whatever the control law we obtain, whether the performing index what we have considered earlier, this one is minimized or maximized. To know that one, we have to check the sufficiency condition. So, what is that condition? Without deriving in details, because we have already derived earlier in some few situations. So, we have to form what is called this matrix H of this del u of t, then this will be symmetric matrix as we have already seen, del x of t, del u of t plus del square h del u square of t. So, that matrix dimension, if you see this, since x dimension is n and u dimension is m. So, this dimension will be n plus m, that is the symmetric matrix. So, this is called has what is called a matrix which is a symmetric matrix, and that matrix we have to check whether it is a will give you sufficiency condition, and what is sufficiency condition will give you whether it is a maximum or minimum. If this matrix is positive definite, then we will get the what is the minimum value of the function. If this matrix is a negative definite matrix, then we will get a what is called positive value, what is called maximum value of the function. Let us see this one. We know, since we know the expression for h, we can easily compute this term, and this term, and this term each is a matrix of proper dimensions. So, if you compute this one, now you see this I will get it q of t, this I will get 0, because I am differentiating with respect to u and then with respect to x. This is also 0 and this is we will get r of t, and that this is r of t. And in order to become the function that is objective function is maximum or minimum, it depends on the nature of this matrix. So, this nature of the matrix, if you see this one, this matrix we have considered, if you consider this is a positive semi definite, this is a positive definite matrix, this matrix is always is positive definite matrix. So, if this matrix is positive definite matrix and which is obvious this okay, and we have selected the Q state weighting matrix and the what is called input weighting matrix based on some physical considerations this thing. So, this will be greater than 0. So, the objective function value that will get it, that is will be equal to what is the, it will give you the minimum value of the function obviously. So, this implies that this must be so, this implies that matrix, that this matrix must be greater than equal to 0, that del square H, this del square of t, del square H, del x of t, del u of t, and this is the symmetric of that one, the star I can write it, then del square H, del u square of t must be positive definite for minimum value of the functional, minimum value of the of j star of j, you write j. So, this is the necessary condition. So, if you select q is positive definite and r is positive semi definite, r is positive definite, this ensures that we will get minimum value of the functional. So, let us take in one example and illustrate that and if you see this expression, it is enough, more stress you can give it in order to become a positive definite. This is enough, R must be a positive definite, this is enough. So, let us solve this problem by using what is called a numerical example. See how to solve the finite time regulator problem by solving a by considering a numerical examples. So, you consider our example is this x 1 dot is equal to x 2 and then x 2 dot is equal to minus twice x 1 of t plus 2 x 2 of t plus 2 u of t with initial condition, that initial condition x of 0 is equal to x 1 of 0 plus x 2 of 0, which is given to you 1 minus 2. So, our problem is to find out the control of u such that the performing index and the performing index, this performing index is minimized. This find a controller u such that this performing index is minimized subject to the condition of that dynamic equation. So, this is our is given is x 1 of square of 6 plus twice x 1 of 6 x 2 of 6 plus twice x 2 square of 6. This is the terminal cost. The 6 indicates at time t is equal to 6, the terminal time, and initial time is t is equal to 0 is given condition, plus half that integration 0 to 6, then twice x 1 square of t plus 3 x 1 of t into x 2 of t. Let us call this half is not given. We have to formulate this problem keeping half. So, let us call it is not, half is not given. So, this is equal to then your 0.5, that is 2 x square, then 2 x 2 square of t plus 0.5 u square of t whole dt. This is the performance index. So, if you consider this is in our standard format, that means half you have to keep it here and multiply it by 2. So, this will be 4, 6, 4, 1. So, we can just write it in short compact form x, x transpose x has a two component x 1 and x 2. So, this we can write it, if you see this one we can write it 1, 1, 1 and this is 2 is x of 6. This is we have written in quadratic form x transpose p x form plus the I told you multiplied by half, that divided by 2 multiplied by 2. So, half 0 to 6, this will be 4. So, the 4, then this will be a 6, 3 is here, 3 is here, that we have expressed earlier how to convert a polynomial, quadratic polynomial into a matrix and vector form, and this is 4, 4 is here multiplied by x of t, here is I missed this one, here is x transpose of t, agree, this one plus this is multiplied by 2, multiplied by 2 divided by 2, that means it is a u square of t whole dt. So, immediately you can find out, you see from this expression, if you write it in that these two equation in compact form, I can write x dot is equal to 0 1 minus 2 plus 2 into x of t plus 0 2 u of t. So, this is our, if you see this is nothing but our A matrix, this is nothing but our B matrix, agree, and this quantity is nothing but our f of t, f, this weightage is given at time t, and this matrix is nothing but our q of t, which is equal to q, because it is not a function of time, and this r is nothing but equal to 1 here, weightage in the matrix, that means weightage in the control vector is 1. So, I can write it now is like this way. So, you can write this is into this form. Note, f of t is nothing but a, since f which is nothing but a 1 1 1 2, just see from the last equation, then our q is, we got it 4 3 3 4 and our r is equal to 1, because it is a scalar input this. And if you look at this expression, if you look this expression, the matrix open loop system, when there is no control effort is applied to the system, that open loop system, that A matrix is unstable. If you want to find out the note eigenvalues of the matrix, you will find the eigenvalues of A are lambda 1, lambda 2 is equal to 1 plus minus j this. So, this is the unstable open loop system, open loop eigenvalues are this, then matrix A is, matrix A dimension 2 by 2 is unstable, and this matrix is what, if you see 1 1 minus 2 2, this matrix A matrix is this one, agree. So, it is unstable. Naturally, we have to use and control law, so that the closed loop system response is stable one. And not only this, that we have to restricted that our terminal cost is given. So, within a time t is equal to 0 with the initial condition this, the final time at t is equal to T f is equal to 6, the state should come near about the that value near to 0, this one. So, so now let us solve these problems, how we will solve these problems. This. So, u star of t, that our optimal control law, this is nothing but a R inverse B transpose P of t x of t. This is our control law, and we know R, we know B, and the state you can find out by simulating the system, or from the system you can get the information of x t. So, now what is this, how to find out P? The solving the matrix dynamic Riccati equation or dynamic matrix Riccati equation. You just write it, dynamic matrix Riccati equation. So, this equation, what is that equation? If you see this equation, or you note it, our R is equal to 1, B is equal to 0 to this, and our Riccati equation P dot of t is equal to minus A transpose P of t, because our A is a constant matrix. So, we omit that symbol A of t, plus P of A minus P B R inverse B transpose P of t, this is function of t, P is a function of t, that P of t plus Q, agree. This is the matrix Riccati equation, dynamic matrix Riccati equation. This you have to solve with the knowledge P of T f is equal to f of T f. So, this value we know it from here, f of t is this one. So, let us see how to solve this equation. So, our P of t, since P is a symmetric matrix, I can write the each component of P like this way, P 1 dot P 1 2 dot of t, since it is symmetric, I can P 2 1 I can write same as P 1 2 of t dot, and then P 2 2 dot of t, this left hand side is equal to minus, then you write it that one A transpose, A is our 0 1 minus 2 2, the transpose will be 1 0 1 minus 2 2, this is nothing but our A transpose. Then P 1 1 of t, P 1 2 of t, P 2 1 of t, P 2 2 of t. Since P 1 and P 2 P is symmetric matrix, I will write is P 1 of t. This is A transpose P of t, agree. Then P of t, P 1 1 of t plus P 1 of t plus P 1 of t, P 2 2 of t into A. A is, if you recollect, our system matrix is minus 2 1 0 1 minus 2 2, then minus P 1 1 of t, P 1 2 of t, P 1 2 of t, P 2 2 of t, P B, B is 0 2. If you see our B is, this is our B 0 2, then R inverse, R is 1, R inverse is that is. So, this is a, this is P of t, this is P of t, this is B, this is this one is R inverse, then R inverse B transpose 0 2, which is B transpose, then P, and P is 1 P 1 1 of T, P 1 2 P 1 2 T, P 1 2 T, P 2 2 of T, plus Q. Our Q is, if you see, this is P of T. Our Q is, if you recollect that our Q is 4 4 3 3, symmetric matrix 4 4 3 3, this, then whole bracket. So, now you just write, you say this is a symmetric matrix of this one. As I mentioned earlier, if the matrix dimension is n, then how many differential equation you have to solve, which are coupled to each other, n into n plus 1 by 2, that you have shown. Now, our n is in the present case is 2. So, 2 into 2 plus 1 by 2, that we have to solve 3 equations. P 1 1 dot one expression we will get from the left hand side and right hand side, P 1 2 another expression, P 2 2 dot another expression. So, 3 equation we have to solve. So, this with P T F is equal to, if you see 1 1 1 2, which is nothing but a FTF value. PTF value is same as FTF value. So, with this knowledge we have to solve it. So, now we write this after solving this one, because you just multiply the right hand side matrix all these things, and equate the position, the left hand side 1 1 position and right hand side 1 1 position. If you do this one, then you will get it, you will get P 1 1 dot of T is equal to 4 P 1 2 square of T plus 4 P 1 2 of T minus 4, and we know the our initial condition for this one, we know initial means not initial, final terminal condition of P, we know that I can write it P 1 1 T f is equal to 1. Then P 1 dot of T we can write, but this I am getting, I told you, you are getting by equating left hand side and right hand side by simplifying this whole right hand side expression into a matrix form, equivalent to a matrix form, this 2 by 2 matrix form. Then you will get P 1 2 dot is equal to twice P 2 2 of T plus 4 P 1 2 of T plus P 2 2 of T minus twice P 1 2 of T minus P 1 1 of T, and that value and minus 3 with P 1 2 of T is equal to 1. Agree? Then P 2 2 dot of T, you will get it 4 P 2 2 square of T minus 4 P 2 2 of T minus twice P 1 2 of T minus 4 with P 2 2 of T f, this is T f, if T f is equal to 2. Agree? So, this equation, you see there are 3 first order differential equation, but they are coupled to each other, and we have to solve. For solving this one, we must know the boundary condition, and we know the final terminal condition of the matrix P or each element of this one P 1, each element of P we know this one. So, we have to do backward integration, and not only this set of equation, if you see, these are the nonlinear differential equation, dynamic differential equation. So, let us call this is equation number 1, this is equation number 2, and this is equation number 3. So, solving nonlinear differential equations 1 to 3 backward in time with the given final condition, means P T f is equal to F T f is equal to, in our case, is 1, and our final condition is what? 1 1 1 2. So, one can solve this thing either two ways, either analytically, which is very tough to solve this one, or one can solve this one by using numerical techniques. So, I leave this problem as an exercise, solve this problem what is called numerical method to find out the trajectory of P 1, find out the trajectory of P 1 of t, P 1 of t and P 2 of t. So, I leave it this exercise, this one, to find the trajectory of this one starting from T f to T 0, means T 0 is equal to 0 value, this trajectory. If you solve these problems by numerical methods, the nature of this response, agree, what you may get it from this one, let us call this is the time, and this is I am plotting the P 1 of t, P 1 2 of t, then P 2 of t, I am plotting this one. Now, see the value of P 1 of T f value is equal to 1, as you know from the terminal cost, this is P 1 P t of P T f is equal to F T f is equal to this one. So, P 1 T f is equal to 1, P 2 T f is equal to 1, P 2 T f is equal to 2. So, our P 2 T f is equal to 2, P 2 T f is equal to, sorry, this is 1, this is 2. So, let us call this is, if it is a, this is 1, this is 2, this is 3, this is 4, and let us call this is 1 2 time 1 2 3 4 5 and 6 7 and this way. Now, you see this one, our final condition on P 1 is where it starts from here, agree, and let us call the solution of this one. If you do the backward in time integration, this solution of this differential equation, if you do by numerical methods, that means by using the what is called your Rangauta method for solution of differential equation, and if you use this terminal condition, let us call this, you are getting like this with the solution. This is corresponding to P 1 t, and P 1 to t, P 1 to t also starts from here, P 1 2 also starts from here. Let us call this solution is something like this, and P 2 starts from 2 here, and let us call this solution is something like this, and this is I am showing the nature of the solution, is not the solution corresponding to the problem what we are now discussing. This is not the solution of this, agree. So, this is the your solution for P 1 t, and this is the solution of P 2 of t. So, if you solve this set of equation that what we have considered now here in backward integration, backward in time, then trajectory of P 11 you will get like this way, and trajectory of P 12 you will get like this way, the trajectory of P 2 lets this way. It is not the I have shown the nature of this one, it is not corresponding to the problem what we have considered. So, I have given you the exercise that you solve it the P 11, P 12, P 22 dot using the final terminal condition, agree, using this final termination condition as well as use the numerical method, say the Rangauta fourth order method, or simplest way you want to solve, if the sample step size is very small, you can use the what is called the Euler's method also for solution of these three differential equations. So, once you get this solution, you store. How you store this one? Let us call I am storing the P of t. How we are storing it? And P is having how many elements? There are 4 elements are there for this particular example. So, you start the 4 elements of this one, that is you see here at time you store it this one P 11 6, P 11, P 12 6, P 2, P 12 6 and P 22 6. With the knowledge of this is given, with the knowledge of this one, with the knowledge of this one, okay, then you find out P 115, P 125, P 2, P 125 and P 225, agree. So, this next you store it P 114, P 124, P 124, P 224 and so on, and last what will get it P 110, P 120 and P 120, P 220. In this way you just store it, agree. So, this competition you have to do offline competition and then you store it in a memory. Whenever you need it, let us call I want u of 0 when to complete minus R inverse B transpose P of 0 into x of 0. So, you retrieve this information P of 0 information from this stored memory from this one and then get it this one. Now, how to find out y u of 1 is again R inverse B transpose P of 1 x of 1. So, P of 1 is retrieve this information from the stored memory, agree. So, this is P of 1 stored and then x of 1 how will you get it? By simulating that one x of this, or from the system you are getting the information of x 1 of t. So, x 1 of t, then in this way you just solve this problem to get it that one, agree. So, in general that this is the procedure how to solve the finite time regulator problems. Next will come the what is called stability analysis of finite time regulator problem, stability analysis. So, next is stability analysis and next is stability analysis of finite time LQR problems. We will be using Lyapunov, direct method. This analysis is very straightforward. If you see, let us consider our system equation x dot is equal to A of t x of t plus b of t u of t. This is our system state equation. And if you use the value of u of t, then you will get it is nothing but a x of t, b of t, and u information is minus r inverse of t, r inverse b transpose p of t into x of t. So, this and this if you club together, you will get A of t minus b of t, r inverse of t, b transpose of t, p of t into x of t. Now, see, this is our, if you say this is our closed loop systems dynamics, closed loop system matrix. Now, I want to study the stability of these systems. Let us consider the Lyapunov function as b of x of t is equal to x transpose p of t x of t, and say p is what is p you have considered is a positive definite matrix p of t. Let us call this is the Lyapunov function we have considered. For any this function you say when p is greater than 0, this function value is always positive for any value of t, all these things. Now, this nothing but a energy function. In Lyapunov function, this is because this energy function value is either positive or 0, it cannot be negative this one. So, with this one, if the system is stable, that if the system is stable, the energy should decrease with time. That means V dot must be negative value, and suppose the system is excited with the initial condition this, whether the system will be stable or not, you can say that if the energy contained in the system due to the initial conditions, whatever the energy, that energy should decrease with time. That means, V dot must be negative. So, this x of x dot of t, we can write it now. If you differentiate this with respect to time t, then we will get the three terms associated with this one, x transpose of t, p of t, x t plus x transpose t, p dot of t, x t plus x transpose of t, p of t, x dot of t. And we know the expression x dot of t expression of the closed loop system, let us call this is equation number 1, we know x dot expression is that one. We replace wherever when we will get the expression for x dot, you replace by equation 1. So, using and using p dot expression is that A transpose of this p of t, let us call this is equation number 2 plus p of t A of t minus p b r inverse of t p v, then star b transpose p of t plus q of t. Use this expression p dot expression and x dot of t is equal to x dot of t is equal to, we got it that one, x dot expression what we got it just now we have seen it A of here x dot expression this, or you write it x dot expression A of t is equal to B of t R inverse of t plus B transpose of t P of t into x of t. So, using this expression and this expression in this expression, we will get finally after simplification we will get finally that one. You see, using p dot x dot in equation 2 using p dot and x in equation 2 we get, using p dot x dot expression in 2 we get that one minus x transpose of t, then P of t, B of t, R inverse of t, B transpose of t and P of t plus Q of t whole into x of t. This must be negative definite. In order to become negative definite, because B dot, if it is a system is stable, then B dot must be a negative definite. So, in order to become negative definite, this must be a positive definite, because it is preceded with the minus sign. This must be a positive definite. So, Q is, if you see the Q is greater than equal to 0, positive definite, and this R is positive definite. This implies R inverse also will be a positive definite matrix. So, clearly from the expression of 3, clearly from the expression of the 3, that whatever the logic we have put it, Q is a positive definite matrix, positive semi definite matrix, R is positive definite matrix. So, R inverse also positive definite matrix, it is preceded with a matrix and its transpose, post multiplied by its transpose and pre multiplied by that matrix. So, this matrix also will be a positive definite. That means, we can say M transpose P M, this matrix, if P is greater than 0, this implies that M transpose P of M also greater than 0, means positive definite. This we have used it here. So, clearly one can say, clearly if R is greater than 0 and Q of t is greater than equal to 0, then Lyapunov condition, Lyapunov condition is satisfied and the LQR controller or the closed loop system is stable. So, this. So, the stability of the now this is the stability of them. Now, let us call, if you are interested to find out what is called the, as I told you, if you use the what is called our finite time regulator problems, that the way we solve it here, it is obvious that you have to check it what is called the sufficiency condition. That means, whether the control law will give you the minimum value of the functional or maximum value of the functional, that you have to check it, and that one can check with this matrix, and this is called the Hessian matrix. Hessian matrix, that Hessian matrix must be a positive definite for functional value to be a minimum, and we have seen that it is enough to check. Let us call, if you select the R of t and Q of t is, R of t is positive definite and Q of t is positive semi definite, that it ensures that function value, what a functional value you will get it minimum. And stability analysis also shows that this R of t greater than if it is there, clearly the closed loop system or LQR controller designed stabilize the our original systems, because if you see our original system is unstable. Now, with this controller we can able to stabilize the systems. So, next question comes. So, as I mentioned is in the algorithm, if you see this algorithm, step 4 of this algorithm, that the optimal value of the cost function is that one. Okay. So, how to prove that one? This is next we will consider competition of the optimal cost. Since we have got the what is called that our control law u of t, that must be satisfied our what is called subjective, that our statement of the problem is like this way: design a controller u such that the performing index what is we consider will be minimized. That is our problem. Find a control law u such that the performing index is minimized, and this u must satisfy this our its own dynamic equation. That means, it must satisfy the constraints. So, naturally the trajectory what we will get it corresponding to the optimal control law, that must be that a of t x star of t plus b of t u star of t must satisfy that equations. That means, this implies that x dot of star of t minus a of t x star of t minus b of t u star of t must be equal to 0. Since with the knowledge of the optimal control law u, the optimal trajectory we got it, and that must satisfy this our own dynamic equations. Agree? This is our condition. Based on this one, we will derive the optimal value of the function. Agree? And that we will discuss next class, that how to derive to get the value of optimal value of the function that I have considered, that j optimal value of the functional j of this is equal to half x transpose of t 0 and p of t 0 x of t 0, that portion we will derive next class. Now, look this, if you know the initial state of this one, which you know from our statement of the problem, and if you know p of t 0, I know p of t f, t is equal to t f final value, then p of t 0 we can find out by from the solution of matrix Riccati differential equation in backward in time and store it p of 0. Then this product of this one is a scalar, and that will give you the optimum value of the functional. So, we will stop it now.